So today we're going to continue with the exponential and logarithmic equations. Okay. So let's say if you have two exponential terms. Or expressions. But they have the same base. That's the key part. If they're equal if the expressions are equal. Okay, but you have to remember the base can't equal 0, and it has to be greater than 1. Well, not really greater than 1. It can't be a fraction. It just can't equal 1. Okay. So in other words, what this is saying is if you have some base to the power of x equal to some base to the power of y, then those two exponents have to be equal in order for that to be true. Yep. Actually, this should be greater than 0. There we go. And a little greater than was up there somewhere. All right, so let's say, for example, let's say if you wanted to solve for x, you had 6x equals 36. Okay, I'm just assuming you're not just solving it in your head. Excuse me. Okay, so we know that 36 is equal to 6 squared. Okay, so that means we can rewrite this as 6x equals 6 squared. Okay, now your bases are the same, which means for this to be true, your exponents have to be the same. Okay, so that means that x is equal to 2. All right, so let's say if we have, for example, if you want to solve for x, 64 to the x power equals 16. Okay. So here, we can actually rewrite both of them. Remember, 16 is equal to 4 squared. And 64, remember, that's just 4 times 4 times 4. So that's 4 to the third. Let me make that x a little, there we go. Okay, so that means 64 to the power of x equals 16. You can make that 4 cubed to the power of x equals 4 squared. Okay. So we know just the power rule for exponents. That's 4 to the power of 3x. Equals 4 squared. Okay. Once again, if our bases are the same, the only way that can be equal is if your exponents are equal. Okay. So in this case, 3x would have to equal 2. Divide both sides by 3. X equals 2/3. All right, so any questions on that one? Okay, so kind of the goal here is to get the bases to be exactly the same. Okay. All right, so let's say, for example, if we have 9 to the power of 2x plus 1 equals 81, and we wanted to solve for x. Okay, so for this one, the first thing you'd notice is that 81 is equal to 9 squared. So that means you can rewrite this as 9 to the 2x plus 1 equals 9 squared. Okay. Which means that if your bases are the same, the only way this can be true is if your exponents are equal. Okay. So that means 2x plus 1 has to equal 2. Okay. Subtract 1 from both sides. 2x equals 1. Divide both sides by 2. X has to equal 1/2 for that to be true. All right. So any questions on that one? Okay. Oops. Okay, so let's say, for example, say we wanted to solve 4 to the x minus 5 power equals 64 to the x plus 2 power. Okay, we want to solve that one for x. Okay, we do the exact same thing. First thing we want to do is to make our bases match. Okay, so you notice that 64 is equal to 4 to the 3rd power. Okay, so we go ahead and just rewrite it. Bless you. So 4 to the x minus 5 equals 4 to the 3rd power to the x plus 2. Okay. Which, once you just simplify the right, you have 4 to the x minus 5 power equals 4 to the 3 times x plus 2. Okay. So now we have the matching bases, which is what we want. So the only way this can be true is if the exponents are true. So that means x minus 5 has to equal 3 times x plus 2. Okay, we just solved that like we've been solving it forever. Go ahead and distribute our 3. X minus 5 equals 3x plus 6. Okay, go ahead and subtract x from both sides. That cancels out. So you have negative 5 equals 2x plus 6. Okay, go ahead and subtract 6 from both sides. Okay, so that gives you 2x equals negative 11. Divide both sides by 2. X equals negative 11 over 2. All right. So any questions on that one? Okay. All right. Okay. Now also what you want to remember that e to the natural log of x equals x, and the natural log of e to the power of x equals x. Okay, so basically they kind of cancel each other out. Okay, and we're going to use those two to kind of solve a couple of exponential problems. Okay, so let's say, for example, if we wanted to solve 100 equals 20 times e to the power of t. Okay. Now, if you have a problem like this, the first thing you want to do is you want to get your exponent alone. Okay, so that means we have to get rid of the 20. Okay, so if we have our 100 equals 20 e to the power of t, just divide both sides by 20. Anything divided by itself is 1. So we end up with e to the power of t is equal to 100 over 20, which is just 5. Okay, we have e to the power of t equals 5, which gets us really close, but we want to solve for t. Okay, so if we're going to solve for t, your next step would be to apply natural log to both sides. Okay, so that means if we have the natural log of e to the power of t, that's going to equal the natural log of 5. Okay. Now remember, the natural log of e to the power of anything, let's say x, it's just going to equal x. So that means the natural log of e to the power of t is just going to equal t, because these two are going to cancel each other out. So t equals natural log of 5. All right, so any questions on that one? And I know in some of the homework problems, they'll ask you for the decimal number to so many places. You just plug that into your calculator. But on the exam, this would be your final answer. All right. Let's say, for example, let's say if we wanted to solve, let's say 3e to the t over 2 equals 11. Okay, just like before, your first priority is to get the e by itself. E 3 to the t over 2 equals 11. Just divide both sides by 3. Okay, so you end up with e to the power of t over 2 equals 11 over 3. Okay. Once again, we just apply natural log to both sides. Okay, so that gives us the natural log of e to the power of t over 2 equals the natural log of 11 over 3. Okay, so we know the natural log and the e cancel each other out. So that gives us t over 2 equals the natural log of 11 over 3. And we multiply both sides by 2. T is equal to 2 times the natural log of 11 over 3. All right, so any questions on that one? All right, so let's do one more. Okay, so let's say if we wanted to solve e to the power of 2x minus e to the power of x equals 56. Okay. Now you want to remember that e to the power of 2x is just equal to e to the power of x squared. Okay. Now with this one, since you have e to the power of x squared minus e to the power of x equals 56, you can either use substitution or you can kind of use it the same way. Either way, just depends on which one you're comfortable with. So if you wanted to, we can let y temporarily equal e to the x. Okay. So you end up with y squared minus y, subtract 56 from both sides, minus 56 equals 0. Okay. So we know we have to find two numbers that multiply to equal our c, and those same two numbers have to add to equal our b. Okay. So for this one, -8 and +7 looks like it would work. Okay. So this just becomes y minus 8 times y plus 7 equals 0. Which means y can equal 8 or y can equal -7. Now we know that y is equal to e to the power of x. Because remember, that was just temporary. So that means e to the power of x can equal 8, or e to the power of x can equal -7. Okay. Which is okay, but we don't want to know e to the power of x. We want to know actually x. So we'll apply natural log to both of them. Okay, so if we have the natural log of e to the x equals the natural log of 8, or natural log of e to the x equals the natural log of -7. Okay. So for the first one, we already know these two kind of cancel each other out. So we know x equals natural log of 8. For this one, remember, you can't have a negative value inside of a natural log. So this is actually not a solution. Because remember, it has to be greater than 0. Okay, so natural log of 8 is your only solution. Okay, so remember, so it's really possible for even both of them to end up being negative, and you wind up with no solution at all. So you want to make sure that whatever's in that natural log is positive. All right, so any questions on that one? All right. Okay. Okay, so let's say as a quick reminder, that a equals p e to the RT. Remember, that's exponential growth. Uh-oh. And a equals p e to the negative RT. That's exponential decay. All right, so let's say if we have the problem. Okay, so let's say a sample of bacteria is growing at a rate of 8% per hour. Compounded continuously. Okay, so how many hours will it take for the sample to double? Now remember, our P, that's our principal amount, our starting value. Remember, R is our rate of change, or interest, or rate percentage. And remember, that has to be in decimals. Okay. Now, the only thing we're missing our A, and we're missing, well, we're solving for T, so but the only thing missing is our A, as far as like the general idea or our amount. Okay. Now for your principal value, they really didn't tell us. So if they didn't tell us, then it's equal to some unknown. Okay. Now our rate, they did tell us. So it is 8%. So it's 8%, which is 0.08. All right. Now for our amount, again, they didn't tell us, but they did tell us they wanted it to double. So if they wanted it to double and your initial amount is X, then that would be 2X. Okay, so they actually gave us just enough. Okay, so since we know it's going to grow, we're going to use the growth formula. Okay, so that means A is equal to our principal times e to the power of RT, which becomes 2x equal our starting value, which is x, e to our rate, 0.08, times t. Okay. So if we divide both sides by x, we actually end up just e to the 0.08 t equals 2. Then we just apply our natural log. All right, so those two kind of just cancel out. 0.08 t equals natural log of 2. Natural log of 2 over 0.08. All right, so any questions on that one? Okay. Let's see, pick a good example here. All right.